Hello and welcome to our last topic in this derivatives unit. So we had our derivatives unit and then we've had several units on applications of derivatives. We just got through the curve sketching unit, so we spent several weeks about curve sketching. Now we have one final topic is optimization problems. So it'll look and kind of feel like related rate problems where you have a word problem, you have to try and set up what you're solving for. But really, we've done optimization problems back in grade 11 pre-cal, except back then we didn't call them optimization problems, we called them min-max problems. So remember those fun word problems we did back in grade 11 where you found min or max values? Very similar idea. But this year, or in calculus, we're going to solve it using calculus method by using derivatives. We didn't know what a derivative was back in grade 11 pre-cal, but now we do. So when you start your word problem, you want to read through, figure out what you're given, what are you trying to solve for, same way as related rates. Then your next step, assign variables. So the same thing as related rates. Draw a diagram, assign your variables, figure out what you have, what you're solving for. And then again, number 3, figure out what relationship there is between all this information. What's the equation we're going to use to solve for that? What is trying to be optimized? So what is being optimized? And then find out what equation or relationship there is between what you're optimizing and what you're given. And then this has to be in one variable. It's the same way we did it in grade 11 pre-cal. Your equation has to have only one variable. When we did related rate problems, we had multiple variables, right? But here, it's only one variable. So that'll be the fun part, doing some rearranging. Then step number 4, you get the first derivative, and from the first derivative, you'll get your critical numbers. And then from that, you're going to figure out where your min or max values are, and then test the values. So pretty straightforward. So we're just going to end this unit with some word problems. So we're going to do 3 together. Just like related rate problems, the more you can do, the better it is, right? Just the more you practice, after a while, you'll start to recognize certain patterns, certain formulas, things like that. So we'll do 3 kind of classic examples of optimization problems, and hopefully that helps. I've written some things already on the board just to save us some time and space because I think it is pretty straightforward at this point. So again, I've kind of summarized the word problems. I do have them written out fully in your notes. I think we did this question exactly in grade 11 pre-cal. I don't know if you can see the top of the phones. So we are finding if the sum of 2 positive numbers is 16, what's the smallest possible value for the sum of their squares? So we did questions very similar to this back in grade 11 pre-cal. So step number 1, identify your variables. So we're going to let our first number be x. So then we need a second number. So you could call it y, right? X plus y are equal to 16, but you can't have a y value. You have to have everything in terms of x. So if our first number is x, and they add together to get 16, our second number is 16 minus x. So this is our first number, that's our second number. So like I said, you have to have it all in one variable. Okay, and then the question says the sum of their squares. So that's what we're optimizing, right? We want the smallest possible value for the sum of their squares. So that's what we're optimizing. So my formula for the sum of their squares is I just take the sum of their squares. So this is a pretty easy one to start with just to give you the general idea. So you take the first number, the second number, you square each of them and add them together. Then I did the work. You can check it to make sure it's correct. You just multiply through, combine like terms. So our equation for the sum of the squares should be 2x squared minus 32x plus 256 if my math is correct. Then we take the first derivative. So you guys should be experts at first derivatives now. So I did that already. The first derivative would be 4x minus 32. Then we set that to 0 and our critical number is 8. Then we answer the question. Now be careful, make sure you answer the question. Some people might stop there and go, oh, I know the first number is 8, we're done. But remember, what's the smallest possible value of the sum of their squares? So don't forget to reread the question and make sure you've answered it. So if our first number is 8, then that means our second number is also 8. But the sum of their squares, 8 squared plus 8 squared, 64, 64 is 128. So I know I went through that pretty quickly, but I think it's pretty straightforward. That's a nice, easy one to start with. So you need to figure out what your starting equation is that connects them. I'm optimizing the sum of their squares. I have the equation, but I needed to figure out how to write it all in one variable. Once you have your equation, get the first derivative, get your critical numbers, and then make sure you answer the question. I think we did a question very similar to that back in grade 11 pre-cal, but obviously not using first derivatives. Okay, our second example, the area of a pen. Remember we did several of these back in grade 11 pre-cal. Sometimes we were putting fencing around all 4 sides. Sometimes only 3 out of the sides needed it. There's a question like this in your textbook. I'm not sure if we did it. So we did questions similar to this back in grade 11 pre-cal. So we have 750 feet of fencing to use, and it's going to be a rectangular area, and there's going to be 4 pens made, and they're all of the same dimensions. And we want to know what's the largest possible area. So what are we optimizing? We want to optimize the area. If we've got 750 feet, what are the dimensions we make to get the largest possible area? That's our max value, right? Our min-max word problems. Okay, so I didn't do all of this. I did some pre-setup, but we'll go through this together. This one I'd find easier to make a diagram, right? You've got a rectangular field. You're making 4 pens. And what's the area? So area is length times width. But in this question, well, you could have used L's and W's. I used X's and Y's. But again, as long as you're consistent with your work. But this is a problem, right? We have X and we have Y. We can't have X's and Y's. We have to have them all in the same variable. So here's the fun part. How do I express Y in terms of X? So to do that, we know that we have 750 feet to make all these pens. And then we add everything up. So we've got 1, 2, 3, 4, 5 X's and 2 Y's. Oh, I'm not sure why there's 2 different colors there. So that's my equation. Now I have to rearrange and solve to isolate Y. So if I do that correctly, I would subtract out the 5, then I divide by 2, and then that's my value for Y. So now in the equation, I can use my area. My X is X, but I can't use Y, so I will replace the Y here with 750 minus 5X over 2. So that's the fun part of these problems. This part's easy, but remember you have to write everything all in one variable. And then we can clean this up a little bit. So when we multiply through, I'm going to skip some steps along the way. If you multiply this through, I guess I could have simplified a little bit, but if I multiply this through all correctly, I should get an area of 375 x minus 5x squared over 2. So I skipped some steps along the way, but in your notes I went through it a little bit more detail. But like I said, you figure it out, you have to isolate y, and then you put it in. Okay, now that I have my area equation, now I'm going to get the derivative of it. I think I might have this on the next slide. Oh yeah, so I just have my starting equation again. Now I get the first derivative of the area. So my first derivative is 375 minus 10x over 2, and then that is just 5. So my first derivative is 375 minus 5x. Now we get the critical numbers for this, so we set that equal to 0. This is easy for you guys. You just have to solve for x. You don't need to watch me do that. So 375 divided by 5 is 75. Whoops, the pen door. Okay, but remember, we're not done the question. We have to remember, what did the question ask us for? We were asked for the largest possible area. So we have x, now we need to solve for y. So just to remind you, oh, there it is, the cleaned up version. I don't think I reduced it in my other slide. So our y value was 375 minus 5x over 2. But now that I know what x is, I can easily replace the x with 75. And if I go through and solve it correctly, I should get a y value of 187.5. Okay, but we're still not done the question. Remember, what did the question ask us for? What's the area? So now we know the x value, now we know the y value. So now we can finally multiply them together. If we go to the next screen, our area is x times y. We just figured out our x was 75, the y was 187.5. So the maximum area we can get with that amount of fencing is an area of 14,062.5 feet squared. So make sure you have the correct units. Okay, like I said, I think a little bit easier than the related rates. One last one. A box. This is the worst box ever drawn. It took me a while to do. So we have a box that's a square base but an open top. And we know that it has a volume of 32,000 cubic centimeters. And we want to know what dimensions are needed to minimize the material use. So if that's the volume it needs to have, this would be a min problem, right? What's the minimum amount you can make that to get that shape with that volume? So I don't think I did any steps here, so we'll begin together. So volume is length times width times height. So in this question, we know it's a square base. So the length is the same as the width, so x times height. But again, we can't have two variables, right? We have an x and we have an h. We need to have everything all in one variable. The question told us that the volume has to be 32,000. So to rearrange to get h by itself, we divide it out. So it's 32,000 divided by x squared. Okay, then I think I wrote too big. So that means when we go back to our original, oh no, we can go to that. So we have our height is written in terms of x. Okay, then I think on the next slide I have the equation. Yes, so the surface area for that shape would be x squared plus 4xh. So that's the formula of a square box with an open top. And x we can keep, but the h, communication error, that we just solved on the previous screen that we had to isolate x or h to be 32,000 over x squared. Again, I cleaned it up a little bit, so our surface area ends up being x squared plus 128,000. I put x to the power of -1. If you kept it over x, that's fine, but I just find it's easier to have that for the next step when we get the first derivative. So the first derivative of this, x squared, is just 2x. Again, the derivative rules, we bring that down in front. So the right amount of zeros, good. Okay, so that's our first derivative. And then I'm just going to write it a little bit easier. So now I'm actually going to bring that exponent down. Well, why did I bring it on top? Just to bring it down. I just found it easier to do the first derivative when I had it like there already. You don't have to. Now I'm going to make a common denominator here. So the common denominator is going to be x squared. So that means we will have to adjust it. So we have 2x squared. Do I have all my zeros? I don't know why I switched from red to blue. And now what we can do is set that equal to 0. Oh, I think I've run out of room here. Again, our critical numbers are coming from the numerator, right? Not the denominator. You can't, that would make the equation undefined. So we set this equal to 0. You guys are probably faster than me at this point. And then we have to rearrange and we have to solve for our x value. So I bring that over. I'm running out of room. So if I've done everything correctly here, my x squared should, my x squared value should be